Hi everyone, in this video I would like to show you an automatic segmentation of the left ventricle on cardiac PET-MR images using deep learning algorithms. This presentation will be more from a practical side where we discuss the implementation of ViewNet with Pytorch. I am Alberto Villagrán. I am a physicist working with medical image processing and learning how to apply these new algorithms in the field. So I'm not an expert in the AI world, and I am happy to receive any suggestion and comment about these implementations. So this will be the main content of the video. We will start looking at why we need a left ventricle segmentation on cardiac PET-MR images. Then move forward to the main part of this presentation. We will discuss about the libraries, the dataset, the model, and the code used for this specific task. Then show some results, and I will share some personal opinions about this implementation. The first question is, why do we need to segment the left ventricle? Thanks to cardiac images, it is possible to characterize in a non-invasive way the current state of the heart of the patients that are under a cardiovascular disease. In particular, cardiac PET-MR images allows us to obtain information about the metabolism and the composition of the myocardial cells, and also to assess the motion, the morphology, and the function of the left ventricle, that is now at the main pump of the cardiovascular system. On the right, we can see an example of a cine image in a short axis view. That is part of this PET-MR image protocol. With this kind of images, it is possible to compute parameters such as volume, mass, and ejection fraction. That is the amount of blood that is ejected to the body in each cycle. Then, in order to calculate, for example, left ventricle chamber's volume, it is needed to identify and delineate the endocardium in these images. For example, if the left ventricle is split into 10 slices, as we can see in the 4 chambers view, where each white line represents the slice that we can see in the short axis view. So if we have 10 slices and we have to delineate this in at least 2 time points of the cardiac cycle, the so-called end diastolic and end systolic phases, we ended up with 20 images to delineate. This is a task that is carried out by the physician in a manual way. So we can imagine how time-consuming it is. So many approaches have been trying to automatize this approach, and deep learning algorithms are part of those. Moving forward to the main part of the video, I'm talking about, in a deep learning terminology, we are going to work with the semantic segmentation task. That is a pixel-wise classification where the output of our model is an image with exactly the same size of the input, but with in each pixel a classification of the object of interest. For example, 0 for the carpet, 1 for the cat, and 2 for the sofa. And in our object of interest, we will have as an image input the short axis view of the left ventricle chamber, and the output should be an image of the same size of our input, but with a classification on where we have background and where we have our left ventricular chamber. In particular, we apply our model in a public dataset that is called Sunnybrook and is part of the Cardiac Atlas project. And this was used for a cardiac MR left ventricular segmentation challenge in MICCAI workshop 2009. It consists of 45 patients with different conditions, and it has cine MR images in a short axis view together with masks or labels of the left ventricular chamber, carried out manually by experts. In this case, we have left ventricle manual segmentation in end diastolic and end systolic phases, so it's around 600 images. Regarding the network of the model that we want to use for this task, we went for the unit that, since it has been showing promising results for more than 5 years in the field of medical image processing. The name of this network is due to the shape of the structure, and it can be split in 2 parts. The first one is the encoder, where with a reduction of the dimensionality, it obtains the main features regarding the input and this specific task. And the second part is the decoder, where the spatial resolution is recovered in order to obtain an output with the same size as the input. So here we can see that in our case, our input will be the short axis view, and our output will be a prediction of where should be the left ventricular chamber. Talking about more in detail about the framework for this implementation, we work with the language and libraries that are open access. In particular, we use Python and Pytorch and MONAI for deep learning libraries, and Pytorch and MONAI and OpenCV for data management. In particular, I would like to suggest take a look at the project MONAI, that is Medical Open Network for Artificial Intelligence. This is an interesting platform that share the different libraries, functions, models that are useful for the different tasks that we need to apply in medical image field. So this is the main scheme of the code. Here we have to keep in mind what are the main objects for a deep learning implementation. That is the loading of the data, the definition of the model, the optimizer, and the loss function. And in this case, I wanted to use the data loader class from Pytorch. And in order to create this object, we need a custom dataset that I call my data, and each class has to inherit the methods from the Pytorch class dataset. This class has to implement the initialization, the getItem, and the length methods. And I also add the function load dataset and augmentation data to properly load our MICCAI 2009 dataset. In this case, the augmentation part, I use random rotation from MONAI transformations in order to keep the rotations exactly the same rotation from the mask and the image. Then I decided to create objects from the data loader with 3 different objects with 3 different type of dataset: the train 80% of data, validation and testing 19% and 1% respectively. Then the network, I defined a class where the model used was the unit from MONAI. I use a dimension of 2D because our input has 2D slices, and a dropout of 0.25 of probability, and the output channels is 1, that means 0 for background, 1 for left ventricular chamber. For the optimizer, I use the Adam algorithms, and for the loss function, I use also the dice loss from MONAI. All of these 4 objects, I feed it to the train model function that is mostly similar to many implementations on internet. Specifically, I use I adapted one from Curtie's code that is in the tutorial of the Pytorch website. And after the iterations, I feed the network and the data loader to a test model function where the score was computed. Talking more in details about my own classes, Here we have my data class and my network class. As I said before, my data was used to feed the data loader from Pytorch, so I need to create this class in a way that it inherits the properties from Dataset from Pytorch 2. And I added this function called load Sunnybrook dataset, where I have to match the specific time point of the mask and the slice from the image input. And also there is some extra functions to normalize scale, to change the scale of the images, and to apply this augmentation process. Then for my class, for the class my network, I decided to use the unit for MONAI, but I code this in a way that I can in the future use different models. So in this case I use a list, and the first element is the unit, but then I can extend to different models and try different implementation and compare the results. And in order to improve the performance of the model, we use the step augmentation, where synthetic data is created from the original one in the training process. In this case, we use a random rotation from the image and the mask. And so we went from the 600 images to 3,500 images. There are other kind of transformation like flipping, zoom in, zoom out, and translations. On the right, we can see some examples. And regarding the implementation, we have to keep in mind that we have to keep the random number used for the angle that we are going to rotate and apply at the same time for the image and the mask. So in this case, the returning part is a dictionary that applies same operation, same rotation to the input and the label. So here we have some results. Our first results of we compare ground truth versus predictions. Above we can see with no augmentation, and below with augmentation, that means using this rotation for the training part. And we can see that the accuracy, that means how similar are the ground truth mask and the predictions, are less accurate with no augmentation than using these random rotations. So we can see that above there is some regions that the network say that is part of the LV chamber, but as we check with the ground truth, this is not the case. Or we can see that the prediction is bigger than the ground truth. And in the case with augmentation, we see more similar masks between both ground truth and prediction. Still some difference, but much less than the above results. Here we have the evolution of the dice score across the iteration of the epochs, and we can compare the results with and without augmentation. Without augmentation, we reach up to less than 0.8 of dice score, but increasing the number of synthetic data that we use for the training part, we ended up to 9.9 of dice score. Here we have the result for different implementations. Without any augmentation, we got 0.7 in 4 minutes, and increasing 5 times or 20 times the data set, we got almost the same dice scores, 0.92, but the time increased considerably. So here we can say that augmentation is needed, but there is a limit of time and the maximum of dice score that we can achieve with this pre-processing. So if we compare with the literature, Here we can see that our unit result was 9.92, and here we see a range of from 0.89 to 0.94. Some of them were using unit or of their own implementation. So we can say that in this basic level we achieve a good accuracy, a good dice score, and that is one of the main points of this unit. And most with this, and also with these open projects that allows us to implement and in our own dataset too. To conclude, I would like to leave some messages. Beyond all of the tips, tricks, and suggestions you can find on different websites, blogs, on internet, and the literature, I would like to highlight that the optimization of organization data is crucial. This was one of the main time-consuming tasks because I need to, in this case, match the exact point of the mask, the position with each image input. The second thing is the augmentation. As we saw in the results, the augmentation helps us to increase the performance, but we have to keep in mind that to preserve the image level matching, as we saw with the rotations, and also the time that this augmentation means in the process of the training part. And last but not least, open access dataset and tools helps to move forward and faster the knowledge in the field. So thanks to this philosophy, we could create this implementation and this video. And thanks you for your time, for your attention. I hope you can learn something new from here. Again, I'm open to any suggestion, comments. I leave here my email, and I would like to especially thanks to Roger, Esteban, and David to help me to work with this implementation.